So there's this new paper out that's making some serious waves. It's proposing a really radical shift in how we see reality. It argues that at the most fundamental level, the universe isn't just described by physics, it's built from the rules of information itself.
And that's really the core question here. It's an idea that could completely reframe quantum mechanics. It suggests that all the stuff we think of as real, particles, energy, even space-time, they're all just expressions of something deeper, the flow of information.
All right, so to really get our heads around this, we first need to take a step back and see how information became such a big deal in modern physics to begin with. You know, for the longest time, we thought of information as something humans create, right? A way to describe the world. But this "it from Qubit" idea, it flips that script completely. It argues that information is baked into reality. For example, in the quantum world, a particle superposition isn't just some weird physical state. It's literally a unit of information, a bit of potential that only becomes real when we measure it. Okay, so to understand how information really runs the show, the paper says we need to get familiar with the three main tools that quantum systems use to manage it all. First up, we've got quantum dynamics. You can think of this as the ultimate rulebook for information. It lays out how information gets encoded into a particle, how that information changes over time, and, this is a big one, how it can get corrupted when it bumps into its environment. That process is called decoherence, and it's kind of like information leaking out of the system. Now, a really important piece of that rulebook is something called unitary evolution. See, in a perfectly closed quantum system, one that's totally isolated, information is never actually destroyed. The process is perfectly reversible. It's like a flawless digital recording. You can play forwards and backwards without losing a single bit of data. And that very reversibility, that's the secret sauce that makes quantum computing so powerful. And you can really see the difference here. A classic logic gate, like an AND gate, is what we call irreversible. If you put in a 1 and a 0, you get a 0 out. The original input information, it's gone. But a quantum gate is unitary, which means it's totally different. The process can always be reversed, so you can always figure out what the original input was. No information is lost, it's just transformed. The third tool in the kit? That's entanglement, what Einstein famously called spooky action at a distance. This creates this incredible direct information link between particles. It makes them act like a single system, no matter how far apart they are. It's this shared information channel that lets us do mind-bending things like quantum teleportation.
Okay, so we've got this amazing quantum information toolkit, right? But here's the problem the paper points out. All the different fields in quantum science are using these tools in their own separate ways, creating this really fragmented picture.
The issue is that everyone's kind of stuck in their own little bubble. The folks working on quantum computing use one set of tools and language, while the people in quantum communication use another, and they're both different from the team studying quantum memory. This siloing makes it almost impossible to get a single, unified understanding of how quantum information actually behaves. And you can see just how fragmented things are when you look at all the subfields. We have totally separate ways of thinking about memory, communication, and computation. And then you get into the really fundamental stuff, like non-Markovian dynamics, which is about systems that remember their past, and time-symmetric physics, which treats the past and future as equals. Each one is tackling a piece of the puzzle, but they're not speaking the same language. This is where the paper proposes something really elegant. It's a new concept designed to build a bridge between all these different fields. And it does it by measuring the informational power of any quantum process. But that begs the question, right? How in the world do you actually measure the power of a quantum process? It's not just about how fast it is or how accurate. How could you possibly create one single metric that lets you judge a quantum memory, a communication channel, and a computer algorithm all on the same scale? Their answer is a new measure they call dynamic informational flow, or DIF for short. You can pretty much think of it as a universal performance rating for anything that happens in the quantum world. It's designed to measure from start to finish just how well a process handles information. So what makes DIF so clever is that it breaks power down into two key parts. First, there's preservation. How good is the process at protecting information from getting garbled by noise and decay? Let's call that its endurance. But then there's the second part, transformation. How skillfully does it actually change that information into something useful, like the answer to a problem or an entangled state? We can call that its skill. A truly powerful quantum process has to be great at both. Now, this might sound a bit abstract, but it is not just a theoretical exercise. Adopting this kind of information-first framework and using a measure like diff has huge, real-world consequences for building the next generation of quantum tech.
Let's take quantum memory, for example. One of the absolute biggest headaches in quantum computing is decoherence, basically protecting your precious information from errors. But by focusing on optimizing the flow of information itself, researchers can design way more efficient error correction codes. And those codes are the absolute foundation for building robust quantum computers.
And the results? They're absolutely staggering. To protect just 12 useful or logical qubits, the standard method, the surface code, needs almost 3,000 physical qubits to do the job. But a new code, this LDPC code, designed using this information-centric way of thinking, it does the same job with just 288. That's a more than 10-fold improvement. It's a massive leap toward actually building a useful, fault-tolerant quantum computer.
Okay, but it gets even weirder and cooler. Because this framework naturally brings in ideas from time-symmetric physics, it actually opens the door to exploring algorithms that aren't just linear. These are called temporally non-local algorithms, and they could theoretically pull in information from across time, not just from the past, but maybe from the future too.
I know. It sounds like something straight out of a sci-fi movie, but this is actually grounded in some pretty serious theoretical physics. Ideas like indefinite causal order or retrocausality are already being explored. They look at scenarios where that strict one-way arrow of time gets a little blurry. This new informational framework gives us the math to seriously ask how an algorithm might actually use those kinds of correlations in time. So, what's the big takeaway from all this? The crucial point is that when you look at the quantum world through the lens of information, you get a much cleaner, more unified, and more powerful model. The focus isn't on what things are anymore, but on what they can do, what they can communicate, what they can compute. The fundamental currency of the universe in this view isn't matter or energy. It's information.
And look, thinking this way doesn't just promise us better quantum computers. It offers a whole new way of seeing reality itself. It suggests there's a deep, informational language that underpins everything we see. And that leaves us with one last really fascinating question. If information is the true language of the universe, what other secrets are just waiting for us to decode once we finally learn how to speak it?